Welcome to Brain Vision.
Two disks A and B, each with given masses, approach each other, collide, and then move off with a given coefficient of restitution. We wish to calculate the velocities just after impact. So what do we know? We know that the x component of A, the velocity of the x component of the velocity of A before the collision will denote prior to the collision with subscript 1 is 6 meters per second, and A moves purely horizontally. The y component of A's velocity, VAy, before the collision is 0, since the motion is purely horizontal. Disk B has x component of its velocity before the collision, VBx1, to be minus 7 cosine 60 degrees, and that's minus 3.5 meters per second. So we're using the left direction as negative here. And its y component, VBy1, is minus 7 times sine of 60 degrees, which is minus 6.062 meters per second. So we have our components of our velocities before the collision. Now, if we use the conservation of momentum and we look at the horizontal components of motion, taking right to be positive, we get the following. We get that the mass of A times its velocity in the x direction before the collision plus the momentum of B before the collision, mb VBx1, must equal to the momenta of each disk after the collision. So that's ma VAx2 plus mb VBx subscript 2. So if we substitute our values in here, we get that 3 times 6 minus 5 times 3.5 is equal to 3, the mass of A, into VAx2 plus 5 into VBx subscript 2. And so essentially we have an equation. If we want, we can call it equation 1. So we have one equation with two unknowns, the final velocity in the x direction for A and B. Now, again, let's look at the horizontal components, but of this time of the coefficient of restitution, E. So E in the horizontal direction is equal to VBx subscript 2 minus the x component of A's velocity after the collision in the x direction, VAx2 all over VAx1 minus VBx1. And so this coefficient of restitution is given as 0.65, and this is equal to VBx2 minus VAx2 over 6 minus 3.5. And so we're left with VBx2 minus VAx2 is equal to 6.175. And we can call this equation 2. So this is another equation which includes the x components of the final velocities of disks A and B. So now if we solve equations 1 and 2, we can solve for these final velocities. So solving 1 and 2, we get VAX2 to be minus 3.8 meters per second, or 3.8 meters per second to the left, and we get for disk B, VBX2 to be 2.378 meters per second, and that's to the right. So we've looked at the horizontal components. Now let's look at the vertical components. So if we take the up direction as positive, and we look at the vertical components, of the momenta, we get that MA into VA Y2, or AY1 rather, since remember A has no vertical components, plus MA VAY2 or actually the two are equal. So the initial Y momentum of A must be equal to final Y momentum of A. And so we get from here that VAY2 is equal to 0, since VAY1 is equal to 0. There's no Y component for disk A. Now if we apply the same to disk B, we get that MB VBY1 is equal to MB VBY2. And from here we can see the masses cancel, and we're left with VBY2, the Y component of B after the collision, is equal to minus 6.062 meters per second. So now we have the X and Y components of the final velocities of A and B, so we can calculate the resultant velocities. So VA2 is simply the square root of the sum of the square of the components. So that's 3.8 squared plus 0 squared. And so we get the final velocity of disk A to be 3.8 meters per second, and that's to the left. VB2 is equal to, again, the square root of the sum of squares of its components. That's 2.378 squared plus minus 6.062 squared. And so VB has magnitude 6.52 meters per second. But we know that VA is to the left, but VB moves at an angle. And so to calculate this angle, theta, so theta B after the collision is equal to the arctan of its Y component over its X component. So that's 6.062 over 2.378. Hence we get theta to be 68.6 degrees.